Hello, this is Rich Whitaker again. This is the second in a pair of presentations dealing with what you can see from maps and aerial photography that you will be downloading onto the Google Earth format. In this particular presentation, we're going to look at aerial photography, wetland maps, and soil maps. Aerial photography has been taken since the 1930s. And Google Earth is doing its very best to get all of the aerial images it can copied and georeferenced so they can bring them to you on the Google Earth format. They're getting a larger and larger and larger number of data sets from all over the world, and it's just fascinating to see both this recent and historical information being presented to us for all kinds of uses. It's really amazing. Here's an example of some from 2010. This is a neighborhood down in the Newport News area. You can see the watercolors. You can see the housing, of course, all the marshes and swamps, the waterways, all different types of land use in the area can be readily identified as to what is available. Now, of course, on Google Earth, you can zoom in closer and closer and closer. Might even be able to see if somebody is swimming in some of the swimming pools. What is very useful from the historical images is to see how the land use has changed. Here, for example, in the 2004 image, that particular subdivision was just under construction. And in the 1990 image, of course, it was just farm fields and woods. One of the really good uses you can have in your project with aerial photography is to use the image as a base map. Print off copies of these for the students and have them plot information when they're in the field onto the map as to where they collected the information. You can also use it to zoom in on some pieces of property and find some interesting features. This is an example of one I found that happened to have a washed area, probably from a lot of rainwater coming down from a particular downspout, and looks like it's creating some erosion problems and sedimentation issues down farther across that part of the slope. So aerial photography is best for land use information, finding waterways, and of course being able to see something about the quality of the erosion situation on land surfaces and suspended sediment floating in the water. Wetland maps are a new bit of information that we've had provided for us in recent years. There is some information, of course, on the topographic maps. The most detailed information, though, is coming from the Fish and Wildlife Service. They have made a major effort in the past couple of decades to map at 1 to 24,000 scale from aerial photography, and they've made locations and classifications of wetland maps available in a number of formats over the years. Now this information is available on Google Earth. Very detailed information is available on a GIS package that they have developed called Wetlands Mapper, and if you want more detailed information than what you get here on Google Earth, you can go to that. For example, several shots from the same area, you can see aerial photography and see what they might have been looking at for their mapping. You can see nice breaks in vegetation between tidal marshes and upland woods and many other features that might be wetlands. Of course, the topographic map has some information. It's not quite as detailed, but some of these maps go farther back and might be more useful for historical changes. Notice the wetlands, of course, in the tidal marshes down, say, around Knott's Neck. But if you look over near where the label of Suffolk is, you can see off to the southeast some of those marsh symbols back in the woods. And clearly that's marking a wetland there in the high flats in that area. The boundary mapping classification that the Fish and Wildlife people have done looks like this. The principal types of wetlands you're going to see in Virginia either start in their classification with an E or with a P. The E stands for estuary or estuarine. The P stands for paludal or palustrian, which means freshwater. If you really want to know what the particular map symbol means, they have a wetland code interpreter that you can type your symbol into. For example, the PUBHX turns out to be Palestrian excavated ponds. A lot of excavated uh, construction ponds in the area would fall under that. So wetland maps are good for the location and the types of wetlands. Soils maps will tell you what sort of material is lying below the surface within the top 5 feet of the surface, where the soil mappers would have drilled auger holes. This information has been gathered over the years, county by county, all across the country, and is now available in a variety of forms. The latest digital form from the Natural Resources Conservation Service, the NRCS, is in a GIS package they have called Web Soil Survey. Google Earth information that we get is a subset of that information. It's very handy, but if you need more detailed information, you can go to the Web Soil Survey that is very easy to use. On the soil maps, the principal thing you see are the boundaries that have been drawn by the soil mappers down on the field by doing their drilling. They would have gone through and put at least one auger hole down to 5 feet every acre across this landscape. Maybe not out in the marshes, but certainly would have done a very good detailed job mapping this area. You will see they have used map symbols in the middle of each of these areas. You'll find a number, and that corresponds to what they call the soil series, the most dominant soil type they found within that particular soil body. If you zoom down closely, and when these lines are up on the image, as you click anywhere on the soil body, you will get a pop-up that shows you, first of all, the colors of the soil down into the ground. And some of these little blocks are horizons that are defined rather precisely by the soils people. These are each of the horizon profiles are characterized by a soil series name, like the Nanzeman, fine sandy loam, as we see here. And the information that pops up on these pop-ups is very useful, but we'll go into even more information from them. So let me show you how you step through these. Let me show you one other spot as well over here in the marsh. We click and we find thick black soil known as the Bohicket silty clay loam. Well, let's look at these pop-ups in a little bit more detail. The Nanzeman fine sandy loam. The fine sandy loam describes the texture. Loam, the major word there, loam is a mixture of sand, silt, and clay. A sandy loam has a bit more sand than the other two components. The fine describes the sand. Looking down through the profile, you see mostly A, B's, and C's as the first letter in those, and it gives you some depths down to almost a 2-meter depth here is pretty common. And you also see down at the bottom a description of where in the landscape these are likely to be found. These are up on top of big broad flats called marine terraces that have formed at the bottom of the oceans that have retreated a long time ago. Now, the Bohicket silty clay loam is a finer grained soil. There's a lot more clay than the other two components in this loam, but there's also quite a bit of silt. See from the colors, it's very dark. Now, as you look at these soil profile labels, or the horizon labels, you'll see, of course, the A's and the B's and the C's usually, but there are a lot of subscripts, and you don't really need to worry about any of these except, for our project, except for the one that's labeled G. G means glade, which comes from a Dutch word in soils that are chemically reduced. These are soils with very, very low levels of oxygen. If you compare the profile descriptions or the horizon descriptions in the Nanzeman, there are no horizons with a G. Well, that's why these soils are rusty colored and the soils of the Bohicket are not. Because the chemically oxidized soils have air getting down into the soil profile over time and oxidizing the iron in the water so that it coats the mud and sand grains. The glade soils are all very saturated, often very close up to the surface, depending upon how high you see that G in the profile descriptions. And these soils, with so much water in them, high up close to the surface have much different chemical properties and have quite a different effect on the plant roots growing in the area. So if you can find soils that are saturated near the surface in your study area, you're going to see a dramatic difference between reduced soils and oxidized soils, both in terms of chemical properties, chemical capabilities, and the conditions that the plants will grow in. One other thing you can see from these pop-ups is down at the bottom of some, you'll see something that says block diagrams pop up. And if you click on any of those labels that they show you there, particularly ones that might say Virginia in them, you will get a picture of what the particular soil profiles look like in that landscape. These are block diagrams showing the physiography and how the soils fit into that. So those are often very useful to visualize where you are with that soil profile. Now, as you go to the top there and would click on that Nanzeman name, you get even more information. The Nanzeman has been described at a particular location, and everybody tries to find if their soils they're looking at match up with all the 10,000 other soils that have been described before, and that's the job of the soil mapper to make those comparisons and classifications. The information here that's most useful for us is going to be down here in the hydrology or hydraulics and erosion ratings. And in particular, I want you to understand what some of these drainage terms mean. Moderately well drained, this is that reddish, orangish Nanzeman soil, is actually sort of a midland level of drainage. Drainage means how high the water table surface is up close to the ground surface typically during a year. Is it close to the surface a lot of the time, or is it at great depth a lot of the time? Now remember that typically they are only boring down about 5 feet with their soil augers, so it's where the soil profile, where the water table shows up in the soil profile. The terms they use are rather interesting. That goes from essentially well drained on one end to poorly drained on the other. Perhaps you find excessively well drained and really, really dry soils like sand dunes, or perhaps you find very poorly drained in some place with ponding at the surface. But for the most part, you would go well drained, moderately well drained, somewhat poorly drained, or poorly drained. Here you can see where moderately well drained fits into that. The wetland or the hydric rating is essentially, is this a wetland soil or not? If it's not a hydric soil, it's either a yes or no answer you get there. Hydric soils are the ones that are usually found in wetlands, and they're almost always either poorly drained or very poorly drained kinds of soils. You'll also see some information here about landscape and geologic conditions. The loamy marine deposits indicate that it's relatively coarse material left on the bottom of ancient oceans. See from the geomorphology, these are coastal plains and marine terraces. You can also get a good deal of information from the measurements that they provide for a typical soil down through that soil at that typical site. There are several things here related to physical characteristics in the top row, and we will principally be able to make use of a couple of these. Organic matter is a very important aspect of the soils. This is typically the black coating on the grains that tends to make topsoil dark, or perhaps peat will become quite dark. But the percentages of organic matter that we have are actually pretty low. 1, 2, or 3% is sometimes pretty high. Sand, silt, and clay make up the soil textures. They give us the clay percentages and sand percentages, and if you want to figure out the silt, you can do the math. pH is provided and tends not to be particularly critical in our soils because almost everything is relatively acidic. Soil pHs between 4 and 5 are very, very common in Virginia, which are all acidic soils. There are 2 K values here. The one that's going to be of greatest interest to us, I think, will be the one called K-sat, or saturated permeability. This is determined by something that can be done by most students, which is a perk test. If you dig a hole down into the soil quite a ways, fill that soil with water, let that water drain down into the soil until it drops quite a ways, then come back several hours later, fill it back up again, and then you could start timing how fast it drops. In this case, it would be dropping at a rate of millimeters per hour. This soil has a relatively quick rate of, say, 100 millimeters per hour, um, and that could be measured over time. Sometimes we'll find soils that are much slower rates. Nutrient characteristics show up in the bottom row. We're not going to make any use of that in our particular project, but you may find students interested in conductivity or calcium carbonate content or so on. You can look up information about that on the charts. So the soil maps then are best to look for the boundaries and descriptions of the soil profiles. You get some landscape information as well as some chemical and physical data, and this is detailed site information. It hasn't necessarily been gathered on your particular site, but somebody's gone and bored a hole there and found what is likely to be present in a lot of those locations where you will go dig a hole. So one thing now to remember with all of these maps is they give you an idea of what kinds of questions you might be able to guide the students to ask. Recognize that not every schoolyard is going to be able to provide opportunities to test every kind of question, but nearly every schoolyard should be able to handle certain kinds of questions, such as where does the rain go and what does it carry? These kind of questions are particularly interesting to students if you can get them to look at the sediment that the water is carrying, as well as the water quality, maybe how it changes going across your schoolyard. Another key question certainly is what will you find when you dig a hole? It's quite interesting to see how the conditions have changed in your schoolyard from the time the maps were made to what it looks like now. Many times construction and erosion and filling have really changed the conditions of the soil. Perhaps the conditions actually will change across your schoolyard in ways that don't show up on the map, and you can identify some different kinds of changes as well. The key kind of changes you may see if you have a wetland can be some of the most dramatic. For example, how does the water and the sediment and the soil and the plants, how do they all interact and affect each other? If you have saturated areas, you definitely can have different conditions in the soil, chemically and physically, that will affect the plants. So one of the things you can really do then is to use these available maps to see what you've got on your property and get the students finding information from the maps to ask questions, plan what they might find in the field, and then go out and see indeed if they really have it, gather some samples, and test the types of information that has been given to them by the so-called experts that have made maps of your particular area. What you're going to see in another series of images then for the next presentation are going to be examples at 3 different schoolyards across the state of Virginia where we have played this game of pulling up the maps and seeing what you might be able to find and interpret at 3 different locations, one in the coastal plain, one in the Piedmont, one in the valley and ridge. Good luck with your projects.